In this first part of the lecture, we will look into the phenomenology of the neurotransmission. That will give us a clue how to extend our passive model that we developed in the last lecture to a nonlinear model. That will be finally the model that describes neurotransmission. Let's first have a look into the experiments. The experiment on the top left, A, is a typical experiment that has been executed. You stick two needles, A and B, into the neuron or into the axon, and then measure the membrane voltage through an amplifier. Now, at the bottom of A, you will see the result. So the pipette in A, measuring the membrane voltage at place A, has a maximum at after 0.5 milliseconds, and then somewhat later you will see the same profile of the membrane voltage at position B. Now, the typical values are that you start with the resting state of the axon at minus 60 millivolt, and then within 1 millisecond, within half a millisecond, it rises drastically to plus 50 millivolt. So we have a recharging of the membrane of the axons. Now, those experiments first have been done on the squid axon, and there we have this change from minus 60 millivolt to plus 50 millivolt. However, doing so in other animals and other species, you will find a very similar behavior. The only change that you will realize is that the maximum voltage or the maximum membrane voltage might be different, and depending on the species, and also the time scales will be also somewhat different. So you see for rat, for example, it only goes up to plus 25 millivolt. For frog, it goes up to plus 30 millivolt. And it looks that the rat is a little bit faster as compared to than squid. Now let's change the experimental setup a little bit by applying an active current through the pipette on the neuron, and follow at the same time the way how the membrane potential or the membrane voltage changes. So in this first experiment, we do a so-called hyperpolarization type of experiment. Typically, the membrane potential is held at minus 60 millivolt. Now we apply a current to the membrane, which pushes the membrane potential even to lower values. And that we do in a square-like fashion, as you see on the top right, in the inset on the top right. And on the bottom, you see how the membrane reacts. So if we give a negative pulse to the pipette, and you see that the membrane goes further negative in this RC-like fashion, and it will recover again to minus 60 millivolt if you retract the current. Now, what is happening when you do the reverse? So you apply a current that forces the membrane potential to go to higher values. Again, the same happens. So it's a typical RC-like behavior. The experiment is called to do a small depolarization of the membrane. Hence, the membrane potential will go up, in this case, to minus 40 millivolt, but there's not a dramatic change. Now, this simple picture dramatically changes if you go to higher depolarizations. So if you give a large depolarization pulse, you will see that first there's this RC-like behavior, but suddenly there's a dramatic voltage increase, up to plus 45 millivolt, by which the axon will react. Now it's important to mention that the membrane potential of the resting state, which is minus 60 millivolt, is about the Nernst potential of the potassium. Where the membrane potential rises up to the Nernst potential of the potassium when we apply this large depolarization pulse. Now if we take a somewhat more detailed view on what is happening right after I apply the pulse. So here you see a pulse series from minus 60 millivolt to plus 90 millivolt, so from low polarization to high polarization. You will see that there's an early current, which is an inward current, so the curves always go downward, and followed by a late current, which is an outward current pointing to the reversed membrane potential. Now, the molecular reason for the two early and late currents can be grasped by the following experiment. Again, we now take a depolarization pulse to minus 9 millivolt, and you see what happens in the case of, in the middle experiment here, A. You see what happens if I have 100% sodium in the solution, and compare that when I reduce the sodium concentration to only 10% of the normal concentration. You see a dramatic change, and you basically will lose the inward current that occurs. Hence, that is the explanation of the early and late currents. So in early after stimulation, the current is dominated by sodium ions, and which is taken over afterwards, flowing inward, whereas afterwards the potassium ions will follow, leading to an outward current. Now, having the split between sodium current, early sodium current and late potassium current, we now can check how those currents behave as a function of the applied membrane potential. Here you see on the x-axis the membrane potential of such a step pulse has been changed, and what you now measure is the current through the pipette that then follows. You see that so if there's no sodium around, so the top curve, we only measure the potassium current, and below minus 50 millivolt, there's no change in the current. If you hit minus 50 millivolt, the potassium current is switched on. Now, if we go to high potassium sodium concentrations, or this is actually the physiological sodium concentration, you see the second current occurring, which is, as we learned, due to the sodium ions and sodium channels. And what you see there is a dramatic change in the sodium current at minus 15 millivolt. So there seems to be a switch in the sodium behavior and the current of the sodium ions at minus 15 millivolts occurring. Now, together with our earlier knowledge that the membrane potential and Nernst potential of the sodium ions is plus 45 millivolts, that of the potassium ions is minus 50 or minus 60 millivolt, we now can extend the model that we made up and come up to the so-called Hodgkin-Huxley equivalence circuit, in which we assume that the two resistances or conductances in that case of the sodium, so G sodium and G potassium, are not fixed resistances, but they depend on voltage. So the hypothesis that we come up with is that the current switches from one ion to the other, and that the voltage dependent conductances will change for the two ions. Now in the next clip we will look for the consequences of this switching conductance on the cable equation.